Your video on, I think, if you wish.
Yeah, at the beginning, let it be
I'll
on.
not make much of a
So,
difference.
can I be seen?
Your voice is a bit low, but I don't know whether it's my audio or yours.
Yeah, it may be my audio. Let me just check.
I need some totally.
Is my the audio now better?
It's a bit better. Put it at maximum and start off, I think.
Yeah, okay. Fine. Okay, so this is Subhashis. I am a staff member of NCRA, and so today I will be describing the experiment 5, which is basically the neutral hydrogen experiment. And the data was originally, this experiment was originally conducted quite several years back using GMRT, and like other years we are of course not going to GMRT or not being able to do it physically, but yeah, even though we were doing things physically till last year, but the thing is, this experiment was not done last year though, it was done several years back, more than 5 years back, but the data was taken from GMRT for about couple of hours. So before I go into the actual experiment and the line shape and so on, I will first describe a little bit about the neutral hydrogen experiment. And so let me probably do one thing. I just switch off my video right now because we are doing a screen share. Yeah, so this 21 centimeter emission, okay, before I go into 21 centimeter emission even, I hope that most of you, the participants basically, know what is a line emission. Line emission typically in a classical sense, if you look at, is basically board transition, which you would have read in your first year and even before, I guess. So in a typical board transition, what happens, which is seen, most of the lines come in ultraviolet and optical and so on, that n is equal to 2 hydrogen level, not hydrogen level, meaning n is equal to 2 to n is equal to 1. If you have a transition of electron jumps from one the board orbital to the next one, there is some amount of energy, which is the difference. That energy comes out, and the delta E corresponds to h nu. Nu is the frequency of the line. Now that is the way typically the emission happens. Now most of this emission, though you would not have come across what is, I guess, what is the line width and so on from the theory, which are typically more covered in MSCs. So, but the main thing is that the energy difference between the two quantum levels in a generic sense gives rise to line emission, and that energy difference delta E corresponds to h nu. H is the you know what is h, Planck constant. So the thing is that the nu is the frequency here. Now, when we talk of H1, then this is not exactly like a Bohr transition. It goes little bit more deeper into the quantum mechanics, but this is the only emission which is very strong and easily detectable in radio band. That's we are talking of this. How it originates, if you really want to understand, you have to go somewhat more deeper into quantum mechanics, into what are the quantum levels and so on. But let me first introduce in the following way that 21 centimeter emission from atomic hydrogen was predicted after the Second World War by someone called Van der Hulst, and it was later detected by three groups. Roughly about, and these three groups I will describe in a minute in the next slide. But before that, let me also give that why are we talking of atomic hydrogen? That atomic hydrogen, in short, most of the astronomers will call it as H1, which some of you may not be knowing. So even in my write-up, I can see that I have written H1. Yeah, any question? Okay, so let me carry on. So in astrophysical situation in our galaxy as such, that roughly about half of all atomic hydrogen is believed to be in warm neutral phase, which is in short called WNM, and it has a temperature of the about 4000 Kelvin. It has got low volume density, that means about maybe one atom per centimeter. You know, on Earth, it may be like 10 to the power 19 atoms per the cc, which is the density of gas in the interstellar medium. That is the medium between the stars in our galaxy. The density of material is much, much lower. It is about 1 per cc. So that is for the warm neutral medium. Now this has got low volume density and it fills large part of interstellar medium with a scale height. Scale height means what? That the density compared to the disk, as you go up along the galactic plane, it starts decreasing. And that decrease roughly becomes half. That means the density is half if you go up by 200% for the Milky Way. So this is roughly called the scale height. That if you go up by about 100 or 200%, the density will fall down by a factor of 2 for the atomic hydrogen. But again, not the whole atomic hydrogen, rather I should say the warm neutral medium. The cold neutral medium is much thinner, meaning that relatively dense, and their scale height is even lower, much lower. So the point is, the reason why we talk of H1 and we detect it so easily from our galaxy is just because about half of all the H1 atomic hydrogen, or rather H1, is a significant contributor in the overall interstellar medium of our galaxy, and half of the warm neutral medium is in the one, the meaning half of H1 is in the warm neutral phase. And the scale height, as I said, is about 200%. Now remember, I am not going to cover all the things related to interstellar medium today, which will be covered on my talk on 6th. So some of these things will become more clearer on that day, I think. But today I'm only introducing the experiment and giving an introduction only to you, Ram. So the other thing is, when we talk of warm neutral medium, you also have to know something, because typically if you divide our the interstellar medium, it can be divided into one, not one rather, sorry. It is basically ionized interstellar medium and neutral interstellar medium. The neutral interstellar medium is what we are talking of, part of which is the warm neutral medium, also cold neutral medium. The ionized gas is different. That we will talk on the 6th, because when things come up on the interstellar medium, generic interstellar medium, things will come up. We are only talking of one part of the, or rather one half of the system, which is the neutral medium involving the hydrogen. Neutral medium can also involve molecular cloud, which we are not going into. So the other thing is the cold neutral medium is distributed in relatively dense cloud, and their temperature is roughly known to be 100 Kelvin. Note that already there are two phases we are talking of the hydrogen itself, the neutral hydrogen. One part is the neutral medium in one component whose temperature, as I mentioned already, is something like 4000 Kelvin, whereas whereas the cold neutral medium is distributed in relatively dense clouds and their temperature is 100 Kelvin, so about 40 times lower. So that is the difference, that they are much colder and their density is much higher. One can ask the question, why is it that if the density goes up and the temperature goes down? It can be shown that the various components of the interstellar medium to be in dynamic equilibrium, meaning these are not really in static equilibrium, we can say, but roughly, quite often they are simplified, saying that they are in equilibrium, and this equilibrium means they should have pressure equality in this case, because if the pressure is not equal, one component is going to expand, which has higher pressure, and forces the another component which has lower pressure to a compact form, where the density increases. So effectively, as you know, that the pressure is nkt, n is the density, k is the Boltzmann constant, and T is the temperature. So if n and T is constant, that means if T is low, which is for cold neutral medium, n ought to go up, and similarly n is much lower when T is higher, which is at 4000 Kelvin. Okay, so that is the observable, basic observable properties, one of the observable, important observable properties of the atomic hydrogen as we see in our galaxy. Now let me go a little bit more, that as I already said, that the H1 constitute one of the main observed component, and the emission comes at 21 centimeter, which is zero point 0.2 meter, or corresponds to 1420.406 megahertz. And this can be shown easily that this is transparent. That means it is optically thin. Most often it is optically thin, and because it is in radio band, you know already that even in general, in radio band, if you consider the scattering property, Rayleigh scattering, you know that it goes as nu to the power 4. That means as the frequency increases, like for example, for light, which comes around 10 to the 15 hertz versus H1, which is 1 gigahertz, let's say, so 10 to the power 9 to 10 to the power 15, almost like 10 to the power 6. So in light, the scattering or equivalent, the effect of scattering, say through Earth's atmosphere or interstellar medium, is ought to be about 10 to the power 24 times smaller. So that kind of scattering is not important, and even the absorption goes down drastically. So the Einstein coefficient, again, you have to look at little bit. I believe already the part of it would have been already covered, that what is known as Einstein coefficient and so on, which is basically the transition probability in short, that between state 1 to state 0. And what are the states? Actually, as I mentioned earlier, I skip a little bit. I will just mention verbally. You can look up the basic quantum mechanics books on it, or you can even check in the web. You will see images and for essentially how they are being hypothesized, or rather how they have been talked of. Is that if the proton and the electron which is surrounding both have a spin, the meaning the H1 has a spin, and if the spin is parallel spin, then that has got a higher energy than the anti-parallel spin. So these two spin, that is the transition which takes place. So between the parallel to anti-parallel spin. So it is a spin flip transition in for hydrogen, and the transition probability is 2.8 into 10 to the minus 15 per second. So you can see that the transition, if you are looking at few atoms, the transition you have to wait for a very, very long time, which you cannot. So that's why if you are taking in a small area in a lab, it is difficult to detect it. And the main reason for it is that if you have to wait for so long, there would be other things which disturbs the spin parallel to anti-parallel state. There will be collisional and other things which will de-excite that the parallel spin. So this was first observed, as I said earlier, that it was hypothesized by Van de Hulst, and it was picked up simultaneously by three groups. One was Ewen and Purcell in Harvard, that is in US, that is in America, by Muller and Oort in Netherlands, and by Pause in Australia. So all the three groups effectively finally brought out the publication together, saying that okay, these are all more or less found independently. So let's have the that we agreed to do it together in kind of thing. So initial work, of course, this H1 after discovery was to characterize the large scale atomic hydrogen distribution in our galaxy. Because as I said, that the atomic hydrogen is an important or a main contributor of the interstellar medium. If you can study H1 as a proxy of our galactic interstellar medium, you can find out how the galaxy gas distribution is there in the galaxy. Okay, so that is what was the main idea. Once those things were done, so that means starting from 1950 to 1970s, this was the main thing to study our galaxy distribution. It is not that it has stopped afterwards, but people understood at least the basics of atomic hydrogen distribution in our galaxy, the galactic arms. There are several arms which we had to basically then consider, considering their different velocities, which the emission comes from the different arms. So we had to basically model it like that. And once this thing was done to a reasonable extent, the emphasis was more to explain the small scale nature, the physical properties of atomic hydrogen, and its relationship with other components of interstellar medium. Okay, so this is one of the pictures which is I have taken from Harshav and Kellerman, and this thing, this particular slide, I will keep in the Google after my talk, so that this can you can essentially share it and check it, because right now one has to rotate and so on. This is LV diagram, which is known as, that is the longitude as a function of, that is, this is rotated right now in longitude velocity diagram. So longitude is along x-axis and y-axis gives you the velocity. The velocity is shown in various grayscale, and you can see that the velocity is pretty high, that it goes from minus 220 to plus about 250 kilometer per second, close to L is equal to 0, which is towards the direction of the galactic center. And as you go away, that much velocity spread is not there. Say if you come to 0 degree to 310 degree, which is about 40 degrees away, the spread has gone down, but there are superposition of multiple components coming from different direction, meaning not different direction, along the same direction of L is equal to 310 degree, which is along a 40 degree away from the galactic center. You are going along the galactic plane and you are looking at that direction. You have a different distances. H1 atomic hydrogen can have different velocities, and all of their components are superposed. So that's why there is spread. Let's say it goes from almost like minus 100 to almost like plus 100 kilometer. But you can see also a systematic variation of hydrogen velocities as a function of L or galactic longitude. That as we look around, if we think ourselves, we are sitting on the Orion arm of the galaxy about 8 kpc away from the galactic center, and as you rotate your line of sight view from the galactic center away, how the velocity will change. So that is the way it is. So now what we do with atomic hydrogen, we have mentioned that how it originates, meaning the basics of how they originate, and why is it important in our for our studying our galaxy. But what is practically one is seeing when one is observing, let's say right now for simplicity, along a particular direction, let's not talk of multiple line of sight or rather multiple components along the same line of sight. Think of a simple direction. And so what we see typically is a line profile or spectrum that is basically along x-axis, you plot frequency, along y-axis, you plot the intensity. So it is typically what you will see in the spectrum plot is the y-axis is showing you the intensity, how it varies as a function of frequency. Now, where the intensity maximizes, you will call, okay, that is the maximum line emission. And this frequency is typically indication of Doppler shift, that is 1420.406. If you are not seeing the peak of atomic hydrogen emission, it means that the line is shifted. How it can shift is because this shift is typically due to velocity. So the atomic hydrogen, for example, if it is coming towards you, then it will be blue shifted. If it is going towards you, it will be red shifted. Red shifted means the frequency goes down or the lambda increases, wavelength increases. So that is the way. And roughly, one can show that 1 kilometer per second, that is c is equal to n lambda. If you use the formula, c is equal to nu lambda, c is the velocity of light, nu is the frequency, lambda is the wavelength. Then one can show that this thing 1 kilometer per second for hydrogen, given that its rest frequency is 1420.406 megahertz, 1 kilometer per second of velocity of the gas will cause a shift of 4.74 kilohertz. That is, if the gas is coming towards you at 1 kilometer per second, the velocity will shift by 4.74 kilohertz. Of course, that will be very small. It is in kilohertz compared to when we are talking of which is in the megahertz. So velocities, these velocities, by the way, are measured typically known as something called local standard of rest. Again, I'm not going to go into something what is known as local standard of rest. These are various issues here in our when you are doing any practical measurements. So those things then has to be kept track of, because when we do the actual experiments in the RPS which you have done before, these were done typically earlier, and meaning these we all go into reasonable depth showing that, but here we are doing more theoretically this time, meaning not going into the actual observation, we are not doing by hand the H1 experiment. But the general thing is that each of our object, that is not just solar system or sun or earth, but everybody in the universe has some velocities. Now depends on what you consider as rest frame. If you are on earth, typically in the namely will call, okay, my earth is my lab frame, so I will measure everything with respect to that. But then we are also moving in our galaxy. So people typically define for galactic observation something called the local standard of rest, which is basically with respect to while we are doing our galaxy observation. And with respect to that, you measure the velocity of the lab frame, and you can also measure the velocity of the object, so that there is no confusion that what reference frame you are using. Now, as such, we know that galactic kinematics as such influence the observations, and natural width, by the way, let me tell you, is very small, that comes from quantum mechanics. and this gives you about number about 10 to the minus 16 kilometer per second. Now this is very very small. You are not going to measure it at all. Now why we then see a line width typically which is much higher, which is maybe of the order of kilometer per second? It is because of the first thing which broadens the line is the thermal motion, that is the thermal motion or the Brownian motion of the gas particles, and that you can show that it goes as 0.09 root t kilometer per second, where t is the effective temperature. So suppose you are measuring a gas whose temperature is 10 to the 4 Kelvin, then square root of t is 100. So that means 0.09 becomes 9 kilometer per second is the line width for a theoretical line width of a object whose or H1 gas whose temperature is 10,000 degree Kelvin. Okay. The line is also broadened by something called turbulence. Turbulence means what? Turbulence means typically that this is random motion, but it is not purely random like Brownian motion. It is more of a motion that where small chunks has different velocities. That's typically what happens. So for example, a small, you are looking at a particular direction, there are five gas clouds, let's say. Each of the cloud can have its own velocity, they are moving. And this velocity also will be happening because there can be local turbulence. That means consider a storm. If you have a storm, there will be turbulence around. This is it forms vortices, it forms complex motion. So this complex motion is typically you can characterize its effect on the line of sight velocities, that this will cause turbulence. And in our galaxy, if you're talking of galactic disk, this turbulence can be of the order of 5 kilometer per second in H1. The other thing which also happens, which we are not going to talk at all today, is galactic rotation. That can also broaden the line due to superposition of components along the line of sight. So all these are important, but they can broaden the line. Now, in general, if one uses the radiative transfer, again, I'm not going into radio basics of I think Deepankar is covering those things, radiative transfers and so on. So the thing is that in general, if kinetic temperature is Tk, brightness temperature is Tb, and optical depth, which we call just characterized by a variable called tau, one can show that T brightness is equal to Tk into 1 minus e to the power minus tau. It can also be shown that for atomic hydrogen, the column density equivalent to which we call as is something which is given by NH1, which is equal to 1.8 into 10 to the power 18 integral over TB, which is basically the integral over TB dV per cm square. So that is the brightness temperature times the velocity interval. You are doing an integration over that. Okay. Now we will go into something which is basically really we are going to you are going to do the experiment on. As you know that the interstellar medium is multi-component, at least have neutral and ionized part, and here we are talking of the neutral part only, not the ionized part. So GMRT was used to basically study the warm and cold phases of the neutral component through H1 absorption and also through emission. And how it occurs, I will just show you. So this is the case. On the left side plot, you see what is typically seen by a single dish. That means that you are observing in a particular direction, and you have basically in a particular direction this single dish is looking at. It is this single dish you can think of like an optical telescope also, that it has basically got a parabolic mirror which converges the light rays coming or the electromagnetic waves coming into a particular area called its focus, and there you have something called a feed, and that feed basically is equivalent of pixel or the camera which you will use in the telescope, in an optical telescope. So that picks up the signal and it basically gives you back effectively an electric voltage, and this voltage is what is acquired as a function of frequency. So you can think of there are many filters in that instrument which basically can divide the area which you can see the x-axis goes from 1418 to 1422 megahertz. So it is about 4 megahertz wide. You have around 128 frequency channel within that, I believe. And so that is what here is being shown. What you are seeing that the line emission, though I have not corrected for any velocity of the lab frame or the local standard of rest, this is raw data. And this raw data, you can see that the left side plot that is basically showing you the emission whose peak is coming more towards 1420.3 megahertz or so. So it is obviously redshifted because the frequency has gone down. So the gas is essentially going away from you. So that's why you are seeing it is redshifted. Now, this may be the gas going away from you. This may be because we did not correct for the local standard of rest or various other things, which would also be part of it. So anyway, leave that aside where the line is expected to come. The main thing here to look at that this line is is not very narrow. This line width goes, or the you can compute equivalently using the Doppler shift formula that what is the line width. This line width is pretty high. You can see that the emission starts from around 1418, 1419.7 megahertz or so, and it goes all the way from 1420.7 megahertz. So the line width is about 1 megahertz, almost like 1 megahertz. So 1 megahertz, I can tell you roughly by an order of magnitude that this 1 megahertz divided by 1 gigahertz is like 1 in 1 part in 1000. So if you take this, the light velocity is 10 to 10 to the power 5 kilometer per second. So this will be 1 by 1000 of that, meaning the total velocity width. So that means as we are seeing emission almost which is spreading 300 kilometer plus minus 150 kilometer per second from the center. So one side will be plus, one side will be minus. So that much velocity spread is involved. In between the peak occurs, the peak has also some width because the data will be there. You can essentially measure, which will be asked basically because which I will introduce the experiment. So this is the left side plot. It gives you in gory detail that how the line looks like. There is a central peak, and then there is on the right side, if you look at the peak, there is one more small peak. It goes down, comes to around 1420.5 megahertz. There is one more peak, or there is one more component of line emission, and then it goes down, falls sharply. The left side is also like, meaning left side also is like that, not that prominent anymore line. But the main thing is that you can see there is multiple component, at least I would say by I 1, 2, 3, maybe four there, five, maybe six components, 6 to 7 components are already there. And there can be a broad emission component on top of it, which goes from almost like 150 kilometer per second. Okay. Now, this is something which you are seeing in emission. Now, what happens is, again, in interferometer, I don't know, meaning I have to go a little bit because this experiment was done using both single dish and also using the array as an interferometer. Now, you may be a little bit worried about interferometer because you don't know some of the very basics, I believe, at the moment. So what we are going to see on the right side plot is the same source, same direction, I would say, towards which you are seeing the emission absorption. Because you see that this is actually, there are two, three things which are happening here. The first thing which was on the left side plot, you are looking at a general direction, which was the direction towards the compact extragalactic source called 1822 minus 096. And the beam is broad because the telescope with the GMRT, its beam is almost half a degree. Beam means the resolution. So it is basically within half a degree, whatever hydrogen gas in our galaxy is coming has contributed in the plot which was shown in the left. Now in the right side is shown in with this interferometer. Now interferometer, what happens is it is like easiest way to think of it as a multiple set of Young's double slit experiment. So that means what? Each of the double slit can create essentially an interferometric pattern, which is like a Young's double slit, goes to grating and so on, but grating is equispaced, whereas the interferometer, not all the antennas are equispaced, but we can deal with that. And it is intentional why we don't make all the antennas spaced equally apart. Leaving that apart, the main thing here to say, that when you go for Young's double slit experiment, depending on the baseline length, that is the distance between the two slits, the fringe width goes down and goes down. So that means here for GMRT, the two baseline or the baseline or the equivalent slits, the distance between each of the slit can be thought of as an antenna, and two antennas can be separated, which are called equivalent distance between the slits are known as baseline length. So this baseline length gives you effectively a resolution which is the one lambda by d. Lambda is the frequency, the wavelength, which is 20 centimeter or zero point 0.2 meter, and d is the distance between the baselines. So using all the baselines means the antenna to antenna joining component, we use to basically make an image of the source. How we make an image, I think has already been told to you. But anyway, main thing to here take home message from here that the resolution of an interferometer is much higher. Here the resolution with GMRT is almost like, let's say, about 5 arc second. So you know, in the same direction towards the source, you are looking at emission which is confined within 5 arc second. Now you know that 30 arc minute is like 1800 arc second. So 1800 by 5 arc second is the resolution interferometer. The total emission which is seen in the direction will go down 5 divided by 1800 whole square, because this is a rotation, right? It is a 2D. You are rotating along elevation, along azimuth basically. So it is a rotation in the two-dimensional plane, theta and phi. You can think of it as theta and phi. So the effective beam area or effective resolution area for the single dish was 30 arc minute square, which was 1800 square. This has got resolution only of the about 5 arc second square. So this is a much smaller number. Here what will happen, that's why that emission is really not seen, because the emission has gone down by almost, like if I would have taken let's say 2 arc second and that was 2000 arc second, is 1 by 10 to the power 6 times lower. So you hardly see any emission. That's why interferometer, when you are looking at a compact object, you are not seeing the emission at all, the H1 line emission from the galaxy. But then how will they contribute? Remember, in that direction, what we are looking at is also a compact background source. Remember, as I said, that the H1 temperature is like 4000 Kelvin in emission, in absorption maybe 100 Kelvin. But the background source which you are seeing, these are called synchrotron emission. I don't know whether you have heard of it, but the main thing is that they are called non-thermal, meaning the process by which it emits is not a thermal emission. They are called high energy electrons, which forms cosmic rays and so on. These high energy electrons really are responsible in that source, in that background or extragalactic source, whose temperature goes to 10 to the power 12 Kelvin. So though the equivalent angular size of the source is so small, but because its the brightness temperature is like 10 to the power 12 Kelvin, which is like 10 to the power 8 times higher, it can be a strong emitter. And that emitter, because it is passing through the atomic hydrogen, though it is optically thin, as I mentioned, but suppose the optical depth is 0.1 or 0.01, it will absorb strongly. So this source, which we are seeing 1822 minus 096, a background compact source, meaning it's like a delta function, you can think of it as, its equivalent flux density called Jansky in the unit of Jansky, which is 10 to the power minus 26 watt per meter square per hertz. So that is 7 units of that. Now that will be absorbed now partially depending on the width. So what has been done further, so effectively what you would see in the raw data would be 7 Jansky, except that where the H1 emission occurs, there will be absorption, corresponding absorption because of optical depth. So those optical depth, because the emission is negligible, you are not going to see it, but they're depending on its optical depth, it is going to absorb part of it. Why absorption? Because it is passing through a medium whose temperature is like for a few thousand degree Kelvin or few hundred degree Kelvin. They're all going to absorb because the equivalent temperature is much lower compared to the background source. So this will be seen in absorption. If one has to do a little bit of I would say equivalent radiative transfer method to understand why it will give rise to absorption. But the main thing is that the source intensity will go down further along in the direction, meaning in the frequency corresponding to the line emission. So around 1420.5 megahertz. So there, what is happening then? That you have basically then absorption, which made it not 7 Jansky, but somewhere it made it 2 Jansky, somewhere it made it 4 Jansky, like that. Now, what we do when we present the data, we subtract the continuum. That means that 7 Jansky is made to 0. So you have subtracted equivalently 7 Jansky from the whole data set. So once we have done that, so while it was 2 Jansky, it has gone to minus 5. You can see it near 1420.3 megahertz or so. The strong negative, meaning strong negative, going down to minus 5 Jansky, it is that. So it was effectively 2 Jansky emission. It has become -5 because we've subtracted the baseline. Correspondingly, you will see very narrow lines in multiple places. Now, one characteristic difference you can see that these lines are much narrower compared to what we are seeing in the left side plot, which is in emission. This right side is in absorption. So this absorption plot is much narrower. It is telling you something that either the turbulence is much lower in this cold neutral medium because this is cold gas, which is really having high optical depth. That's why they are absorbing. And this absorption, which I mentioned, effectively is given by this formula. TB is equal to TK1 minus e to the power minus tau is what is being given by this formula, where tau is the optical depth. So coming back to the plot, so basically you are then seeing lines whose line widths are much smaller and they are pretty strong, deep. That means the tau, for example, goes to 5 by 7. So that means the tau is of the order of 1 here. So it is not optically thin, close to the place where the strong absorption occurs. So there it may be in that narrow frequency range, there are a lot of cold neutral gas sitting along our line of sight. So that has absorbed most of the background emission. So that is what is the case. Now what do we do with the data? I am giving you basically few experiments to be done. I am sure that though I have talked about multiple things today, you won't be able to follow everything. But what you have to do is some practical experience we are expecting you to achieve from here. That looking at these two plots, I will basically go whatever I am asking. And of course, we will discuss further during the tutorial and the talk, of course. That in that figure, which you saw the H1 emission and absorption towards the compact background source, now we assume the spectrum is composed of few lines, that is, each is of Gaussian shape, and this may be sitting on a baseline. Baselines means what? Ideally it should be zero, but in practice it may not be zero, it may be an offset, or it could be a second order term also. Sometimes the instrument may give a dark current, equivalent of dark current, which you have heard of in CCD camera and so on, some of you would have heard of. So that dark current equivalent thing is what is coming out as baseline. And that baseline, if it is not zero, you have to subtract it. Here it looks like the baseline is close to zero, that the both of them plot roughly close to zero, but not exactly zero. That's why. And this, now each of the line you can or the spectrum you can consider as a mixture of several Gaussian, that is addition of several Gaussian. Now Gaussian, how do you represent? You would have heard of basically that it is essentially the line or the I nu. You can write that it is equivalent of I0 exponential the v square by sigma square. V is the velocity, or the nu square, nu minus nu naught square by sigma square, where sigma is the width of the Gaussian. So you have to write several such components. That is basically I01 exponential the v square divided by sigma 1 square, v minus v0 whole square divided by sigma 1 square, plus I02 exponential v minus the v02 minus sigma square, like that. So several Gaussian. So what we are saying is, in practice you have to look at each of these small components as lines. I will show you soon, the once I leave the screen, that how to visualize it. So what I'm talking of, let me try to see if I can do that. Yeah. So you can see the thing, whatever I am touching, you should be able to see that. So where the red cursor is, that is the peak of the line, you can see. So peak of the line is shown by the red cursor, I believe you can see. Now this is one line which you are representing by a Gaussian, then plus a next Gaussian which will have an offset, which is here, the next peak. So that is one. Then there is a third peak which you have to do here, like that. Similarly, there is one more here, one more which is here, and then there is a broad thing. That broad thing goes up to like this. So each will have like the x minus or v minus the v0 square divided by sigma 1 square, plus I naught 2 exponential x minus or v minus v2 square divided by sigma 2 square, like that. So you have to find out each of the component central velocity, which is v1, v2, and what is the width, sigma 1, sigma 2, like that. Remember also this baseline which is being seen, they are roughly is a straight line, but they are not exactly so. So this data is given to you. So what we are going to do is that so this assuming is a composed of few lines, find the frequency and width of each one of them from both emission and absorption. Now this thing will of course go, the data file name you don't have to memorize here. So each of these data files are ASCII files, which will have a column which is giving you a frequency, the first column I believe. The second column will give you basically the y-axis, which is basically uh, this axis, and depending on, this is the x y axis, so it will have the intensity, and depending on the file you may have even two columns. One is showing you for Stokes RR, which is right circular polarization. You may have also data for left circular polarization, and typically you would use just one. I am not asking you to do from both. The idea is to find the peak frequencies, that each of the component frequencies, and their width and their height of course will be there from both emission, and this you have to repeat in absorption also. So in absorption, how it looks like, you have one peak which is here, one which is here, one which is here, one which is here, one which goes here, another is here, then there is one more here, like that. So these many peaks you have to add. In fact, even here one more component is there, and you have to see that whether you can get this going, because sometimes depending on which software you are picking fitting, you have to give guesses of each of these values, v1, v2, v3, v4, like that, and their width also you have to give your initial guesses. So those initial guess, without that you may not be able to get the program fit convincingly. Once you fit with a function fx or f new, you should plot it on top of the data file and see that both of them roughly agree. Okay, now this was the first part. Yeah, so this H1 absorption and emission both are being shown here. So both of these are shown here in the file. This is experiment number 1, H1 line parameter, and it will also have another component called the RMS. So the next question is of course that do the emission and absorption line widths differ greatly? If so, why? So that I have already given you hints that why the one neutral medium, which is seen in emission mostly, and absorption dominates, which has got more tau. That means the absorption depth. So whichever will have more optical depth will contribute, as you know already, that the n or the this thing that the column meaning equivalent density of the one neutral medium is pretty low. So you don't expect one neutral medium to have significant optical depth. It will be really done by the medium which has got high gain or high density. So that's why that is called neutral medium, which has got lower temperature and causes the absorption. So the other thing is also there is one more file in the drive which should be there. So which shows the spectrum of a region determined from a region far away from the compact source across the frequency channel images. So that means if I am basically looking at a point source, I can also make image further away from the point source, how it looks like. So there, I have taken the spectrum along that direction. The advantage of that is really there is no emission in that direction because the point source is absent. There is no absorption because the point source is absent. What you are supposed to do, that along this thing, as you are going, in this x-axis, y-axis will have a small fluctuation. So that fluctuation you have to characterize basically by, yeah, so you have to characterize by something called the RMS. So in the second case, you have to basically find so that is experiment. Sorry, just a moment. Yes, so the second, there is one thing wrong which I should correct here. So this is not 3, this is 2 rather. So this is 2. So this is basically what is it telling you, that is basically to find. So it basically you are supposed to find RMS. Now remember that this RMS can also change when you are doing it. When you are close to the line, you may have a different RMS because there is strong emission, and that you may have also to characterize. That is, the emission here on this part of the line can be much less compared to the RMS here. So you should characterize the RMS close to the line frequencies. That is one part, and further away from the line frequencies. Both are needed to characterize the RMS. Okay. Number 3, which is basically a bit different, and I hope that Avinash Deshpande has already covered a bit about interferometry. So that the idea is here that the calibrated UV data for each frequency channel, which were used for making the spectra, is effectively a Fourier transform of the complex source towards which the observations were made. So then what I am asking is that you can also find the RMS noise using a single baseline, which I have just given antenna number 116 with 30 seconds of data average. So here you can again find the RMS from this file. You can again repeat the same with 5 minutes of data averaged and see using data from the whole array how the RMS compares. So that is the idea. Now what will happen is whole array for GMRT has 30 antennas. It can be shown that 30 combination 2 is basically 435 is the number of baselines you will have when you are adding 435 baseline data together. How their RMS will improve, it can be shown that it should improve a square root of n, and which is n is the number of baseline. So for one baseline which is shown above is a with 30-second data in time domain, when you average for 5 minutes, let's say the same data set, because in 5 minutes you have 30 seconds is half a minute, almost 10 data points, you expect a factor of 3 improvement in RMS noise. And here using the same data sets, so that means it is during the full observation period, which I think is about half an hour or so. So you have to average in time and frequency both, and it will go as square root of nu and t. So compared to 5-second one baseline, here you have to see that whether it is improved by square root of 435, which is a factor of 20. It should have gone down a factor of 20 and another factor of 3 because we are averaging in the time domain. So both will come. So these are the part 3, A, B, C, 3 part. Part 4 is find the RMS noise using a single baseline with 30 seconds. Okay, sorry. Yeah, there is a problem here, I think. Whole array is down. This is a repetition. I will delete this. So this is basically what will happen, that in sector ABC, which I said that using a single baseline, you are comparing RMS with averaged time and averaging over the whole array, how the RMS noise changes. How the other 3 cases compare with what you expect. So that is what the question is really. And number 4, when we go, it is basically another question, not directly to do with the line, but to do with an interferometer, which is that the interferometer has a basic similarity with Young's double slit experiment, and the GMRT data which was used above, the source has been shifted away from the center towards north. This is a hint already given. As will be discussed that the phase phi, so this phase which we are seeing here, meaning which we see in a interferometric data, you can think of it as 2 pi by lambda, d is the baseline length into delta theta. Now this can be shown explicitly where d is the baseline length using the combined data files for 3 different baselines, which you have given in the Google folder, which will give you the values of u, v and w because this is in north, only one of these thing contains this UV and W. I am not talking about today. This again should have been covered in interferometer. The basic thing is, it is the baseline component. One is along east, one is along north, and W I am not talking about at all. W is a different thing. So what interferometer measures is basically the effective amplitude, and the this is actually complex number which has got the visibilities which we call equivalent of cross correlation between two antennas. So this cross correlation has an amplitude and a phase. This amplitude, I'm not asking you to do anything on it. It is the phase which will matter. This phase will change. If the source is at phase center, it can be shown that the phase of each all will go to zero. If the phase is not, that is basically if the source is not at the phase center but is offset at an angular offset delta theta, it can be shown that the equivalent interferometric phase will go as changes 2 pi by lambda into d is the baseline length, into delta theta. Here it will be du, because it is along the north direction, so only u we have to look at, which will matter really. So these are the experiments which I have given to you. Now I can essentially, what thing I should have, yeah. So these are the experiments, and so what I'm talking of, that if this is at an angle theta, so this is for a two antenna whose baseline length is d, then you can think of that you can essentially then draw a perpendicular on this. That is basically that the source is coming from this direction. You can then show that the delay which will happen in reaching, so these are the two rays which are coming together like this. So the extra path which one of the rays has traversed to reach here is basically, this is d, this is theta, and this part can be shown as d theta. So this part is basically d theta, which will be shown here. That is the extra path difference which it has traversed. Sorry, this theta should be defined not from here. Theta is actually defined from the other direction. So I should rather write, yeah. So this is 90 minus theta, then this will go to theta. So basically the delay which matters for an interferometer, and that's why I mentioned that if the source is not meaning away from the center by an angle theta, so how much it offers. So with this I will stop, but you can basically now start asking questions wherever you found it difficult to explain me more, and I can go further details. Huh? Sorry.
Subhashis, you're done?
Yeah, I'm done.
Okay, there are no questions in the chat. So if anybody would like to ask a question, you can put your hand up. Prakash and Jamir can coordinate.
See, my view is we do. My There are no questions from YouTube also.
Okay, maybe they're a bit tired. Okay. Anyway, we'll have corridor sessions as well. So maybe we will just take a gallery shot now.
Yeah, and some of you, if you want to ask question, you can even switch on your the video so that I can see that.